In this talk, I'm going to present the work improved SPSS using complex variables. This is a joint work with my advisor, James Spott at Johns Hopkins University. So our work introduced a stochastic optimization algorithms using the complex value variables. The goal is pretty simple. We just need to minimize a general loss written as L theta here. That can be represented as an expected loss, where we have this theta represent the parameter of interest and V represent some general random effect. And our goal is to find out the actual minimizer of this loss function, L theta. The approach we did has two major parts. One is the gradient free. So the idea is we only rely on a noisy measurement of the function. There's no gradient information, no function structure information, etc. So here we use the notation L hat to represent the noisy function measurement. Know that we don't have any control on the stochastic part. So the V is just a noise that we get from the nature. We don't know the specific value for the noise. We just take a measurement and collect it. The gradient-free approach has much broader applications, especially for complex systems where you don't have the control of the noise, and then the system might be too complex to actually derive any analytical expression for the gradient. Another major applications is in black box optimization, where you just don't have access to the underlying model. Okay. Another part for our algorithm use the complex value variables, which we show that using this new approach, we can actually have a faster rate of the convergence than traditional standard gradient-free approach. And also, which sort of unique here is we are able to estimate a gradient just using one function measurement. So this can help us to have a better instantaneous gradient estimation, especially for non-stationary systems. Okay. Just a quick review on the classic gradient-free approach, which is the simultaneous perturbation stochastic approximation, which is developed in 1992 by Spott. So the idea is pretty similar to find a different method where you took two function measurement at two different perturbed values. So one at theta hat plus some perturbation value, ck delta k, and then another function value evaluated at theta hat k minus perturbation value. Okay, so and then we collect the difference between the two function measurement, then divided by column vectors to ck delta k to get all the components of the gradient at the same time. So this is the name simultaneous perturbation means you don't need to estimate each component separately. You can just do them in one shot. This is extremely useful for high dimensional problems because the number of function measurements is fixed. And then there is some theoretical works to show that the gradient is asymptotically biased and it can have convergence, etc. But then the main difference here is you have to do simultaneous perturbation instead of the traditional finite difference. And then we have another way to estimate gradient, which is called complex step gradient estimate. It also has been developed many years ago, but then it's it's mainly developed for gradient for univariate problems, and then there's no gradient, there's no noise at all. So how this thing works is you have a parameter value theta, and then you add a complex part to it. So that makes the whole argument to be a complex value. Then you take a function measurement at a complex value. So normally, if you put in a complex input for a certain computer program, you expect to get a complex output. So, but then to actually get the gradient estimate, we take the imaginary part of the complex function measurements, and then divide by C to get a gradient estimate. So the intuition behind it is you just apply Taylor expansion on this complex perturbation value, and then you see that some part only contains real values, some other part only contains complex values. But then when you take the complex, when you take the imaginary part, the only thing left is this the part that contains gradient information and some higher order noise. And now this way can sort of get rid of the unwanted terms by free, and then you can directly uncover the desired gradient value. Okay, so the motivation for our work is just to combine the SPSA and the complex step gradient estimate to have an efficient way to estimate gradient in high-dimensional problems. Okay. So our gradient estimate had this form, whereas we're taking the entire vector theta hat k and then plus a complex perturbation value on it, then take a noisy function measurement of the perturbed value, then do things in simultaneous perturbation fashion, estimate all the gradient at the same time. So there's a couple of remarks for this new gradient approach. One is there's only one function measurement. So that's just really useful when you have non-stationary problems, where when you take a function measurement, the system has to evolve to the next state. So you cannot really take two measurements at the same time. Okay. But then you have to be careful here is, even though we reduce the function measurement by half, but then since complex variables has doubled the number of variables, so the actual implementation may be more expensive than real value only operation. Okay, and then to update the theta hat, we just do this standard stochastic gradient descent approach. And note that the gradient itself is always real, so that the theta hat is always real. The only complex part is when we take the function measurements. All right, so there are a couple of important applications for us. Because of the existing complex thing, so it's pretty hard to actually involve with real world system. So you cannot put in a complex level temperature, for example. But then when you have a computer program that you can do simulation, or you can train neural networks on a computer, the complex operation can be legit, and then it will be good to actually apply the gradient descent method. Okay, so there's some theoretical results we did for the complex step SPSA. So the first thing is the bias of the gradient is almost unbiased, because we derived the high order term to be OCK squared. As CK goes to 0, our gradient is asymptotically unbiased. So because of that, it's pretty easy to show that our estimate is it's converging to the true value almost surely. So at this time, those two results are sort of aligned with the standard SPSA algorithms. And then we don't use any extra assumptions than what has been used in classic SPSA and noisy-free complex step gradient estimate. Okay, so the really interesting result is this asymptotic normality, where we're able to show that our rate of convergence can reach the fastest possible, or the optimal rate, which is k to the 1/2. In general gradient-free method, the optimal rate you can get is k to the negative 1/3, and this is also what has been shown in standard SPSA. But here we're able to show that we can actually have a much faster rate. Okay. So the last thing is one quick numerical study. So we studied this Lqr problems. It's a linear systems. So we have xk depending on this system equation, and then we don't have direct measurement on x. We just take a noisy measurement, which is a yk here. So for Lqr problems, we assume we have a linear feedback control which is the UK here, and UK is defined to be negative k times xk. So the goal is to find out the optimal value for k, and to make the k as a vector. We denote the theta here just to vectorize it, and then the goal is to minimize the to find out the optimal k such that the overall loss can be minimized. Where Q and R are both given definite matrix to represent the sort of the weight or regularization terms you want to put on the UK. Okay. To compare to do this in noisy measurement, since we don't have the measurement on X, so we're just using the value for Y directly. So this is our noisy function measurement. And then to compare with SPSA, we just do this for 500 iterations. Know that for each iteration we have different number of measurement, but then since complex is more costly, so for each iteration the computational cost is about the same. So it shows that the complex step has better performance than SPSA. And also another thing to mention is this thing can be extended to time varying loss, where you just take an instantaneous loss, and then to get a noisy measurement, just change X to K, and then a similar result can also hold. That's it.